So we were discussing regarding the relationship between the gain and the directivity as well. So we were discussing, we have started with the realized gain, means whatever we are seeing in the normalized gains, in that case is losses are not accounting, means losses are not accountable, these are not counted at all, and these are ignored, as you can say. But in the case of realized gain, as I have told in the CST Macrowave Studio as well, we will see two types of gain, that is one is gain IEEE and one is realized gain. So realized gain means when the losses are also, or losses are also are considered regarding that. Now the relationship between this gain and directivity, which is given by the efficiency, how it has came. So in this formulas I have considered it, I have shown it that gain is equals to, we all know that whatever the radiation intensity divided by the total input power, accepted power. So P in divided by 4 pi means all over the spherical region. Okay, so that will come as a 4 pi u of theta phi divided by P in. Then further, this P radiation is nothing but the efficiency. Definitely whatever the radiated power is efficiency only, but P in also whatever the power has been given. So efficiency will be, but P radiation again, this if I'll write that input power is of if I'll keep as P in as P radiation divided by ECD, if I'll put this in the first equation, then it will come as P rad divided by 4 pi P in 4 pi multiplied by U of theta phi divided by P rad. And since this ECD, that is efficiency, it is in denominator, so it will goes to the numerator again. And we all know that this 4 pi u theta phi is nothing but the your directivity. Okay, so that in that way we can see is gain is equals to theta phi is equals to efficiency. CD is nothing but 2 points they have considered, nothing else, and d of theta phi. Okay, now further dB scale. What is dB? Because we have seen this dBi, dB gain is defined in the dB, but we don't know what dB is. So dB is nothing but a logarithmic scale. Mainly whenever we are plotting some large quantities like voltage, currents, powers, like that. So at that time we need a scale which can represent these higher value in a very easier way. So that time this dB scale came, which is of decibel, and short form of the bell, decibel. Okay, and further it is given as a name and the honor of Graham Bell only. And generally it is used in every field, either it is in electronics, physics, or any other field as well. Okay, now regarding the dB variants, means other types of dB scale, if I'll say, then it will as come as dBm, dBw, dBd, dBc, means antenna gain versus half wave dipole in that case of dBd. dBw, where W is capital, it is nothing but with antenna gain with respect to the 1 watt power. Okay, and dBm is considers the 1 milliwatt with respect to 1 milliwatt, whereas in dBc compares the antenna power with the carrier power. Now dBi means gain with respect to isotropic antenna. But since I have already told that isotropic antenna is not exist, do not exist in the real life, it's only a theoretical antenna. So you might have having a question that query in your mind that if if a antenna it's not existing in a real life, then why we are considering it in a parameter or a scale in order to represent the gain of practical antenna. So that also I will tell in the coming slides as well. In the next slide only I will tell probably. Then further voltage or current, if I have to measure voltage or current, then it will be 20 log V output divided by V in. And similarly power, if I have to measure, then 10 log of p output power to input power. Okay, now in case of positive value of this dB scale, then it means amplification, and if negative value means depicts attenuation. Okay, now practical gain, antenna gain. Now as I told you that isotropic antenna is having a spherical pattern. Okay, now if it is having a spherical pattern in the 3D way, so in order to represent it in a 2D manner, then it will come as a circular only. Okay, now in case of a practical antenna, it is having some major beam, or you can say the main beam, which consists of the most of the radiated power. Okay, now suppose this is having a isotropic antenna gain, and since gain is having a value of 0 dB. Why? Because in case of isotropic antenna, I told you that it will radiate in all the direction in equal amount. Okay, so if you remember the definition for the directivity or gain, so whatever the ratio of the radiation intensity in a given direction to the average radiation intensity in all over the direction. Okay, so it is giving a maximum direction, maximum directivity only in all the direction. So it will be having a equal amount divided by equal amount, whatever the x by x, it will be equal only, so it will come as 1. Now if I change this numerical value of 1 to the dB, it means log 1, it will be 0, means it is neither producing power, means neither emitting the signal, nor it is absorbing, means minus or plus gain, nothing is there. Either plus 3 dB means it is amplifying, or minus 3 dB means it is absorbing, so nothing is there, but that is not possible. So that's why we are saying that this kind of antennas will not exist in the real life. Okay, then further if I'll say that for the practical antenna, suppose this point source will be same only. Okay, now till this region, till this circular boundary, whatever the practical antenna is producing the gain, that is also 0 only. Okay, so that is also 0 only, so that's why whatever the value we are getting, efficient enough value, that is for outside this region, only. So that is only on practical gain, which is our area of concern. Okay, so that only we are saying that this is having a 3 dB 4 dB gain. Okay, so that's why this till this region it is 0 dB. So in case of dB, I suppose I am telling dB also we can measure, dB also that conversion we can do in any way. Okay, but generally in the most of the scenarios we are measuring it in a dB only. 3 dB attenuation, 3 dB you might have heard about. Okay, so that only we are considering now in this case only. So that's why we are saying 3 dBi means in case of directivity, if I'll say, so 3 dBi means with respect to that isotropic antenna we are having a 3 dB outside this boundary. Okay, so like that you can consider. Now the next comes as reflection coefficient. Reflection coefficient is nothing but the whatever the reflected, we are giving some input power and it is having a reflection. In case of antenna, I'll say whatever the voltage we are giving, so it is reflecting back. So these kind of parameters will say reflection coefficient. Okay, and one kind of S parameter, if you have heard S parameter, S11, S12, in case of two port antenna network, two port device, so it will having a 4 element like S11, S12, S21 and S22. Okay, where S11 and S22 are the reflection coefficient and S21 and S12 will be the transmission coefficient. Okay, this we will see in coming slide. Now in the case of reflection coefficient, it is not possible, we all know that it's not possible, in even though that maximum power transfer theorem we will apply, then also it is not possible to transmit because so many losses will also be there. That losses also we will have a brief on that as well. So this reflection coefficient is having a value as tau is equals to Zn minus Z0 divided by Zn plus Z0, where Zn is nothing but the input impedance, or you can say the antenna impedance, minus the Z0, where is the characteristic impedance. Okay. Now the characteristic impedance is 50 ohm only, and antenna is excited through the standard impedance feed line, and if the impedance is equal to feed line, then tau will be 0 only. And okay, now tau is 0 means your reflected power is 0 and transmitted power will be 100%. If you can see in the in the left side in the box, I have mentioned reflected power. So transmitted power will be 100 multiplied by 1 minus tau square, and return loss is nothing but the return loss in dB is minus 20 log tau. Okay, so yeah, now S matrix, if I'll say S parameter, it is kind of a matrix only in which it will give us the detail regarding the S parameters, that is reflection and transmission coefficient as well. What I have told just now, I have mentioned here. Okay, now this is used at a high frequency because it is easy to use at a high frequency, because anyway we are having other parameters as well, like A parameters, B parameters, like that, H parameters, Z parameters, Y parameters are there. Okay, so but in case of this S parameter, it is easy to use at a higher frequency. Okay, and we can compute the parameters like gain also, and we can plot these two Smith chart as well. Other parameters can be also obtained from this as parameters, that simple calculations will be there, or sometimes tools will also be there that can do these kind of calculations. Okay, now S parameter signifies the mismatching or the reflection occurring from the n port electrical system. Okay, suppose if I'll say for the two port system, it is having a four elements like 2 to the power n, where n is the number of the ports in the electrical devices. Okay, and regarding this SMN means, suppose S12 is written, means power is transferred from port 2 to port 1. Okay, in the right image, if I'll say this DUT means device under test, that will be there, and from A1 to A1 to B2 we are having, so incident we are putting means power we are supplying, and S21 is there, means from port 2 to port 1 it is coming back, means this area. Okay, this is nothing but the S11. Okay, this is also one kind of S11 only, and this is also a S21, means power is transferred from port 1 to port 2. Okay, now this S12 will also be there, where from port 1 to this B1 is transmitted. So okay, from this port to transferred from port 1, port 2 to port 1, one more energy is coming, and port 1 to 2 we are giving. Okay, and whatever the, this is transmission coefficient S12 S21. Okay, and whatever the reflection is there, that is from port 2 to port 1. Okay, these kind of figures you have to understand. Similarly with the case of this as well, whatever the energy we are giving, but whatever the energy we are transmitting, port 1 to 2, 2 to 1, that's why this arrow direction is this side. Okay, now further I'll say this VSWR, that is voltage standing wave ratio. SWR we all know, standing wave ratio. Whatever the waves we are trying to transmit, that these waves are also will have some reflection, and it will take place in that same transmission line also. So this is also, standing wave ratio is also very harmful in terms of this high frequency and even low frequency as well, because it can give more delay to the system, like that. So other parameters are all, other factors are also there. Okay, regarding this S11 and VSWR, each will give at higher application, it will give there is having their own significance. But anyway, in this manuscripts and all, it is not needed to plot both the results, S11 and VSWR both. Okay, VSWR is also related to the reflection coefficient, that is tau, and that tau VSWR is equals to 1 plus mod of tau divided by 1 minus mod of tau, that is modulus of tau, means we are taking the real part as well as the positive part only of the S11. Okay, and further I already discussed that regarding this 1 plus more tau, that if fully 100% transmission has been occurred, means tau is 0, and if it's 0, VSWR is 1, which is the ideal value. Okay, now it is a unitless quantity. Why it is a unitless quantity? Just now if you will say voltage standing wave ratio means maximum voltage to the minimum voltage. Sorry, minimum voltage to the maximum voltage. So all are having voltage only. So that's why it is a unitless quantity. Okay. Now what is bandwidth? Bandwidth, if I say in a layman terms, means whatever the range of frequency in which antenna is resistive and it is providing a acceptable results such as gain and all everything, it is providing an acceptable results, that is called as bandwidth of the antenna bandwidth or the bandwidth of the operation for that specific antenna. Okay, like image I have included in the left side box, which is having a S11 as minus 18 with the frequency of operation as 28 gigahertz. So at minus 10 value, we will say that it is having a range of frequency from minus 10 to 10. Why minus 10 we are considering? Because ideal we are considering at 10 to 12% power is accepted reflection from the power from the antenna, we are considering as a normal only. So that's why s minus 10 we are considering as a 90% power has been transmitted. Okay. Further, further, now next axial ratio. In the right side, I have mentioned it. Axial ratio is major axis of polarization divided by minor axis of polarization. Now remember that in case of theoretical value, if I am telling the axial ratio is equals to 1 for the circular polarization, and 1 to infinity will be elliptical polarization, and infinity will be linear polarization. Okay, but in case of simulation, in case of CSTF Altel and any other software as well, up to 3 dB we are considering as a circular polarization, and after 3 dB we are having it as a linear polarization. Okay, now link budgeting and link transmission. Friss transmission equation. So link budgeting, what is link budgeting? We all know that even though 100%, suppose 100% first of all 100% power only, it is not possible to transmit. Okay, suppose 90% if I am taking, so in that also 90% power has been transmitted to the environment so that it will reach to the desired receiver. Now during the transmission, during the channel propagation or communication, it will face, definitely it will face so much of distortion